Thank you, Miko, for the introduction and giving me this opportunity. Once again, a kind welcome to all in our today's webinar, the first one in the webinar series. That means there are many more yet to come. In today's webinar, I will talk about the PillarHall lateral high aspect ratio structures for the process monitoring in atomic layer deposition or chemical vapor deposition technique. So the main purpose of today's talk is to give an overview about the practical use of PillarHall lateral high aspect ratio structures in your ALD or CVD process. I assume most of you might have experience with atomic layer deposition or chemical vapor deposition, or at least you might have already heard about these techniques and their benefits. The most important merit of this deposition technique is the conformality that they provide. This conformality is very essential and which makes them an inevitable these techniques inevitable in atomic in today's microelectronics. Even though conformality is the most important feature of this deposition process, but monitoring the conformality in this process is not that easy. It is very expensive and it requires it is a time consuming. So in today's talk, I will explain how easily we can monitor or we can measure the conformality of this process using our PillarHall lateral high aspect ratio structures. Before we go into the details of the talk, I will give a short introduction about myself, who am I, and what is my background. So I work as a senior ALD scientist with Chipmetrics, and I come from India, from the southern part of India, a state called Kerala. I came to Finland in 2012. But I got the opportunity to work with ALD in 2018. Sorry, when I started my career as a postdoc in the group in Professor Marit Karppinen group in Aalto University. So here I was working with the atomic layer deposition and molecular layer deposition technique that gave me immense experience in this atomic layer deposition field. Some of the important works that I did where we utilize this atomic layer deposition in the application point of view, like flexible magnets, the development of flexible magnets, and then metallic or intermetallic thin films, and then antiviral coating films or photoresponsive materials. So flexible magnets here, we know that in the conventional magnets, they are very rigid. So some of the applications, for example, utilizing them in flexible electronics, we need them to be in a very flexible manner. So here we were we developed a process for this flexible magnet utilizing this atomic layer deposition, molecular layer deposition technique. So here we were using the epsilon iron oxide as the magnetic providers, so as the inorganic layer, and then in between these two iron oxide layers, we were incorporating incorporating organic layers here in this example, terephthalic acid that provide the flexibility for this otherwise rigid epsilon iron oxide. So we were able to see even when we provide the flexibility, still they act as a hard magnets. So there is no destruction in the magnetic property. And in another studies, we were depositing these zinc iron intermetallic thin films using this atomic layer deposition technique. Then another interesting thing, we were showing the application of this atomic layer deposition technique along with the MLD, this antiviral coating. Here we were, so we talked about this antiviral coating when Corona hit. And then during the time, this curcumin, which has some antiviral properties, came into the limelight. So we were thinking of clubbing this antiviral property of curcumin along with together with this titanium dioxide. Though we were not able to see any much antiviral property, but we were able to see like when we could tailor the visible light absorption property of the titanium dioxide using this curcumin stitching. Then the another area where we utilize this ALD MLD for this photoresponsive materials. So we were using isobenzene dicarboxylic acid, which undergoes these types of trans to cis isomerization when we irradiate with UV light or visible light. And this property can be utilized, for example, developing a photoresponsive magnets, and then also for some photoresponsive photoresponsive MOP structures, metal organic framework for molecule capture or release properties functions. So these were my backgrounds in ALD MLD. So now the importance of today's talk. So why this conformal coating and monitoring is this conformal monitoring is very important. The answer is very simple. Today, we see a miniaturization in the microelectronic devices and also clubbed with these three-dimensional geometries. For example, all the microelectronic devices like 3D NAND or silicon vias, 3D DRAM or 3D silicon capacitor, all of them have these types of 3D geometries, and they have these whole structures, and it is very tedious to do the process monitoring in these types of three-dimensional structures. So I mean, like for this three-dimensional monitoring, for the process monitoring, we need a cross section, and all those are very tedious. And this implicates the importance of utilizing some easy technique for the process monitoring in these three-dimensional geometries. The conventional way of 3D thin film metrology is using these vertical halls. And it has a lot of disadvantages. The main thing is like you need a cross-section for the analysis. So when you do the cross-section, basically you are destructing your sample. And this cross-section is you need some experts to get a very clean cleavage. And you need to utilize very tedious devices like focused band beam or high resolution SEM or TEM, and that can be very expensive. And also you get the data only from a very sliced part of your sample. You don't get full coverage. And another thing is like this process development is very slow. If you don't have these devices like FIB or SEM10 in your facility, then you have to depend on somebody else for this analysis, and it will take days or weeks or months in some cases. And on the other hand, it is very expensive. And one of the other disadvantage, like as you can see, in today's dry etching, the maximum aspect ratio that can be reached around 50. So most of these process, the penetration depth goes beyond the 50 micrometers. So it may be, it is impossible to monitor your process using this vertical test structures. So here we provide a solution for these vertical, to replace these vertical test structures. So we provide this lateral high aspect ratio test structures. The main thing is like, okay, here the aspect ratio was very low, but here we can have aspect ratio even around 10,000. That is more than enough for any process. And then this is very easy way to use, very simple. So that is very you don't need any experts to monitor your process when you use this PillarHall chips. You don't need any analytical devices like FIB, SEM, or CAM, but even this conventional lab tools, for example, optical microscope is more than enough for analyzing your PillarHall chips after the ALD or CVD deposition. And then, as I said, there is no cross-section record. So here, these PillarHall chips have a roof membrane, a silicon membrane, and the other thing is like this is completely of silicon, these test structures. So here you can easily remove this top roof silicon membrane using an adhesion tape approach once after your ALD or CVD deposition, so that you can expose your deposited area for any analytical devices, for example, optical microscope or any other optical microscope, sorry, any other analytical devices that is compatible with the planar sample. So like, as I said, here it is quite a time-consuming process here, the analysis. But if you use the PillarHall chips, you can even get the results with less than 5 minutes. So it is very fast as compared to any of these vertical test structures. How this works? So here there is a schematic illustration of the PillarHall chips after ALD or CVD deposition. So this is the PillarHall chips, and this blue area represents the deposited film. So here this is the top roof membrane of the PillarHall, and you can see also a film grown on the top roof. And but we are looking for this the film that obtained in the cabbage, in the trench, inside of the trench. And this area represents the opening area, and so we measure the penetration depth starting from here till the end of your film. And this is we denote here, it is denoted as XP. It denotes the penetration depth. And H represent the gap height. So that means the distance from the surface of this PillarHall chips to this the top roof. So once after your deposition, you just remove this top roof membrane along with this film using this adhesion tape method, so that you can just expose your the film that grown inside the trench to any analytical device. For example, here you can see like we are using an optical microscope to see this deposited area, to visualize the deposited area. So here this colored, like where you can see a color that shows like where you have the film. So this is the opening area, I mean from here to here, and here the membrane edge location. That means where we start measuring the penetration depth. So from here to here we measure the penetration depth is like this area, this length. And we can easily utilize the optical microscope analysis to measure the penetration depth. So as you can see from this graph, so here we were aiming at a 15 nanometer thick film. So you can see like from the membrane edge area, till to this distance, so say like around 80 micrometers, the thickness is say like around the expected like around 50 nanometer, and after that the thickness is reducing, it decreases. So here there is this arrow mark. This indicates what is the penetration depth at 50% of the initial thickness. So somewhere here, if you see like the 25 nanometer will be the half of the initial thickness. So what up to what length this filling with a 25 nanometer you can see. So I mean like up to around 100 or 110 micrometers. So the PD50 in this case is around 150 micrometers. So you see the initial around this 50 nanometer, then you see the decrease in the film thickness, and then where the film ending. So this can be utilized for the reaction process, for example, for the kinetic studies of your process. This gives a schematic illustration image of the PillarHall chips, a chip layout. So this area represents where shows like where you can hold the chip using the tweezer. I mean, this area there are no test structures, so you can hold the PillarHall chips in this area, but not in this area because all the test structures are in this area. So if you hold this area, you are basically damaging the test structure. So in order to avoid the damage, you always hold the PillarHall chips in this area where we mentioned this cleaving notch. So as I said in the previous slide, the gap height is 500 nanometer. So that is also mentioned. So we have a so here we have a different cavities. So you can see like there is a very long one, then the cavity length decreases. And also this aspect ratio also decreases along to the left-hand side. So I will talk more about this one in the next slide. So here, this aspect ratio is like around 10,000. So this is the one with the largest cavity length. So that means the length is around 5024 micrometers. And here this width opening, I mean this width opening. So this is like 100 micrometers. So here the W100L502 stands for the opening width. 100 is for opening width, and 5024 is the cavity length. Similar for in this case is also here the opening width in this case is 90 micrometers, and the cavity length is around 1020 micrometers, and it follows like that. So, and you can see this is a one. This in this case it is not mirrored. That means you deposit only in this direction. So as you can see, like we have only one long test structures, the cavity with a 5 millimeter length. But in other cases, like in this case, this is mirrored. So that means you will see the filling in both directions because we have a common opening, so that open to both the left and right. So in this case also, and similar to this W80, W70, and then you can also see in the W60, so on. So the main aspect, the feature is like there are different types of the different cavities with aspect ratio ranging from 10,000 to 2. So as I said, like we can monitor almost any process because of this very large aspect ratio feature. Now the product and its delivery. So here so we usually send the PillarHall chips in a vacuum release tray. Each tray consists of 5 PillarHall chips, and this PillarHall chip size is 15 into 15 millimeter, and they are in this vacuum release tray. That means they don't move during the transport, so they will remain intact, very stable there. so there won't be any damage. So usual delivery is like once you make the order, then we start the process within 7 days if we have enough PillarHall chips in the inventory. So we send them in these types of packages. So that means they will be very safe. So once you receive the PillarHall chips in this vacuum tray, then you can go for the ALD deposition. As I said, just always make sure that you hold the PillarHall chips at this place. Don't go to this area. And then you can take the PillarHall chips into your ALD or CVD chamber. You don't need any pre-treatment. And we advised to use like these types of carrier wafer or the pocket wafers, so you can keep your PillarHall chips like they are bonded, so they won't fall out from the pocket. So, and this is very advisable for especially for the conformal ALD processing, and that I will talk. That I will talk about it in the later slides. So once after the deposition, you can easily remove the top roof membrane using the adhesive tape that I showed previously. So then you can expose or you can measure the deposited area using any of your analytical devices. So since these are like planar samples, we can utilize any analytical devices that is go with the planar samples. So I said we don't need any sophisticated instruments. If your filling thickness is above 15 nanometer, then we can use this optical microscope for the for the for the measurement of the penetration depth. So I have given two examples. So once you remove the top roof membrane, then you expose this area. So basically, this part represents this area. So you can see like here we have used in this analysis we have seen the pictures from this opening with the W90. So that means it's a mirrored. It have this opening that opens to both direction. So and you can see like this is very conformally both left and right side. And similar for another process. For in this case, like this was for epsilon iron oxide, and this was for the aluminum dioxide deposition. So this penetration depth also depends very much on the materials and also the ALD process used. For example, you can improve the penetration depth by increasing the pulse length of your process. So yeah, then another thing is like because these two measurements done in two different labs, so and using two different optical microscope, that is why you see this under different settings you see a different color. It has nothing to do with your measurements. I mean, like it doesn't influence on the penetration depth. So whatever the optical microscope you use, you can easily see the penetration depth of your process, though you see different colors. It also very much also this color also very much depend on the material you used. And if the filling thickness is less than 15 nanometer, then the solution is like using this line scan reflectometer what we have. So the thing is like it operates in the UV-Vis near infrared region. So we can easily identify the penetration depth for ultra thin films. For example, this is an example from a titanium dioxide deposited with a 5 nanometer thickness. So this having a spot size is around 7 micrometers. And from here, we can easily calculate the PD50 value, for example, as we calculated from the optical microscope image. And you can also visualize the conformality of penetration depth using a top view SEM. And the main thing, I mean, like as compared to the vertical structures, so there we need, there you definitely need SEM or TEM, but then you need also cross section for your you should need a nice cleavage to get a very clean picture. But here you don't need any cross section. You can just use a top view SEM, and from the contrast SEM image you can identify, you can visualize the conformality of your process. For example, in this case, the penetration depth is around something around 175 micrometers. So this was for a 5 nanometer thick aluminum dioxide. So you can easily see like the conformality of your process. Then you can also club any other analytical devices. So for example, here our customers like Kokusai, they were monitoring their process for this silicon nitride, and for their process they were using this XPS line scan for the elemental composition monitoring. So the best thing is like you can measure the elemental composition as a function of the penetration depth on your in your sidewalls. So this is not possible with any other technique, because here this is the sample is like a planar one, so we can use any analytical devices, for example, XPS or Raman or top seams, any technique that is go well with the planar substrates, samples can be utilized here. So you can easily measure your elemental composition, which is very much required for any process development. Yeah. So I told previously, like we can utilize this PillarHall chips for the wafer level conformality. So here we are showing an example, like using a 200 millimeter silicon wafer. We use in this case we used 7 PillarHall chips in different positions, and we did the ALD depositions, and then we were measuring the penetration depth. So we could see like how the penetration depth vary with the position. So you can, so with this data, you can easily measure the wafer level conformality of your process, and you can also compare the wafer level conformality for the different ALD tools. For if you have a different ALD tools, then how the conformality vary with each tools, that is also can be measured using this technique. And we also offer pocket wafers for the semiconductor process. We have starting from 150 millimeter, then a 200 or 300 millimeter pocket wafers. And all these pocket wafers, we have 9 pockets, and each of them with this PillarHall chips, this 15 into 15 test chips. So this PillarHall chips is bonded tightly with the pockets using a liquid glass adhesive. So there is no organics involved. So that means it is safe for using ALD deposition. So there is no outgassing in this when you utilize these pocket wafers for your processes. So we like at least up to 450 degree, there is no outgassing. So most of this ALD process, like up to it's 450 is really good for most of the ALD process. So this can be easily utilized for any of these process development. Another thing is like another important thing is like we also have this comparison tool. So once you use PillarHall chips in your process and you measure the penetration depth and utilizing this data, then you can easily predict the penetration depth of your target structures. Your target structures target structures can be either holes or squares. But then with this data and the data that you need the hole diameter or this diameter of your square of the hole, and then the penetration depth you will get from the PillarHall chips after the ALD or CVD deposition. Then you can also measure the film thickness, and then using the Gordon equation and giving these inputs into our calculator. So this yellow represent the inputs. You will get you can predict the penetration depth of your process. So in this case, the gap height is 500 nanometer. The PillarHall chips obviously 500 nanometer, and the measured film thickness is 20 nanometer, and the measured PD, the penetration depth for the process, say like 100 micrometer, and we already know the diameter of the hole. If it is 200 nanometer, then you should expect a penetration depth around 17.4 micrometers. So this is utilized vice versa. I mean, with the using this hole or squares and doing ALD deposition and measuring measuring the penetration depth. You can use this data for predicting the penetration depth in the PillarHall chip. So in that way, as I mentioned here, we can compare the penetration depth between the trenches, or trench to hole or hole to trench, and so we can also utilize this information, or we can utilize this calculator for designing the experiments. So with this, we have already seen the benefits. So the most important benefit of utilizing these PillarHall chips, it is very quick, and so it will fasten your R&D process, especially in the fab. So there you don't need to do any cross section, and even you can repeat your process and measurements. Like even you can finish within a couple of hours or within few days. But in the other case, if you have a vertical test structures, you need weeks or months to optimize your process. So this and moreover, this PillarHall chips go very well with ALD, atomic layer deposition, atomic layer etching, or chemical vapor deposition, and also molecular layer deposition. And the major thing is very easy to use. So it is very user friendly, and the results are derived in a very short span of time. I mean, less than 5 minutes is required to get the results if you have very thick film. Yeah. So, okay, thank you all.